And as we are still very hopeful that in the future we can have an in-person meeting on modular flavor symmetries, we have postponed it again for some time, which we don't know yet when it will happen. And then we will bridge the gap, and we do that by organizing 2 lectures, one of them today and the other one of them tomorrow at 4 o'clock in the afternoon, our time. And so we will have one discussing modular flavor symmetries, a review lecture on from the bottom-up approach, and one from the top-down approach. And today we have the one by Gui-Jun. At given point, you have to tell me how one pronounces your name correctly. At least I think your last name I pronounced correctly. Professor Ding got his bachelor degree in 2002 at the Inner Mongolia University, and then he moved to the University of Science and Technology of China, where he got his PhD in 2007. And then he stayed there as a postdoc and climbed the academic ladder till he became a member of the faculty, where he is still nowadays as a professor in Hefei. His current research interests are in neutrino physics, flavor symmetry, and fermion mass model building. And I think he made important contributions to the field of modular flavor symmetry. In particular, I remember the double cover of the finite modular groups, the discussion and the construction of the corresponding modular forms. Most recently, he was also working on the automorphic forms of the Siegel modular group, and also the question of CP symmetry and symplectic modular invariance. So we are looking forward to your talk. We will have allocated in some way 90 minutes plus questions. We start somewhat late, but of course this is not a big problem. And typically we were thinking that we have a coffee break in between, and this will be the decision of the speaker when he decides when there will be a good time to make a coffee break. So please, Professor Ding, go ahead and tell us about recent developments in modular flavor symmetry.
Firstly, I have to thank my Professor Michael for inviting me to give a review, give a talk in this virtual mini workshop. Michael asked me to give a review about recent development of modular flavor symmetry, but I have to admit, many people is much better than me in this task. So if I mix something or I have said something wrong, please tell me directly. And this talk is based on my recent work on modular flavor symmetry with my collaborator Penchen, Fruchley, and Stephen, and many others, and some others, my student. And firstly, I start from the standard model flavor puzzles. And the standard model flavor puzzles is this one. Some picture is I sometimes my, and we start from standard model flavor puzzles, and for the first one is about the mass. The mass have been precisely measured by both the quark and the lepton, but still the neutrino mass we don't know. The absolute value is still neutrino mass. The absolute value of neutrino mass is now known, and we don't know it is normal order or inverted ordering, but we know its value, its order or electrovolt. And another aspect of flavoring puzzle is mixing. You can see the quark mixing is a CKM mixing matrix, and the lepton mixing is an MNS mixing matrix. And you can see this is the square of they are 3 by 3 unitary matrix. The square of each element, the element, the largest, how large with the area of each element you denote how large it is. you can see the secant matrix is almost diagonal, and the largest one is a capable mixed angle between the first and the second generations. And the lepton mixing matrix, lepton mixing is a large mixed angles, and the atmospheric mixed angle is about 45 degrees, and the solar mixed angle about 40 more than 30 degrees. The smallest one is the reactor mixed angles, and this mixed angles is the mass and mixing parameter is a fundamental parameter in particle physics, and you can see besides the gauge coupling and the Higgs valve and Higgs mass and the Higgs vacuum expansion values, all other free parameter is mass and mixings. So all the most free parameter in the SAN model come from mass and mixings. So the question is, in SAN models, the mass and mixing are determined by equal coupling constant, but it is not constrained by by SAN model gauge symmetries. In principle, values, and we have to decide its values from the experiment measurement. So the question is, who ordered that? This question is asked by Astori Rabi after the discovery of muon. That means we want to know the principle behind the mixing, behind the flavor, behind the mass and the mixing. So, and at the moment, several possible meanings, several possible approach to understanding the flavoring puzzles. And the most popular one is based on symmetry, and the symmetry can guide us to understanding the flavor mixing, origin of flavor mass, Fermi mass, and flavor mixings. And usually, we don't know the fundamental principle, underlying fundamental principle, but symmetry have already helped us a lot. Most important is it can reduce the free parameters. The two important symmetry is the Guts and flavor symmetry. For Guts, it is unified quark and lepton within one Guts multiplet or few Guts multiplet. So it can relate the quark and leptons, but it have no explanation for the flavoring structures. Why the flavor mixing have the observed patterns, but it have already answered some things. It reduced the parameter for some special for the simplest Guts. To understand the flavor structures, we have to relate the three generations of the fermions. That is the flavor symmetries. So besides the gauge symmetry, it is usually called vertical symmetry and the flavor symmetry. It is horizontal symmetry. It is related to three generations of fermions. So the most general, the general idea is we extend the Yukawa coupling in SAN models by after the flavoring fields, the vacuum expansion values, they reproduce the Yukawa couplings. That means at a high energy scales, we have some flavor symmetry, and the flavor symmetry have to be broken down by some potentially breakdown by some vacuum expansion value by some vacuum expansion value of flavors. So the Yukawa coupling would be the function of the flavors. You can see for the lepton sectors, the first term is for charged lepton mass, and the Yukawa coupling depend on some flavors. After the flavor got valves, they give some special structures of the charged lepton Yukawa couplings. And similarly for the neutrino sector, they are spontaneously break down by some other flavors, and the flavor got valves, the Yukawa coupling become some common Euro numbers, and this is for the neutrino mass and the flavor mixings. And the recent development is a modular flavor symmetry proposed by Frutley, and they simplify the procedure greatly. That means they assume the flavoring phi in the charged lepton sector and the neutrino sector are the same. a complex modular. It parameterize the shape of the extra dimensions in string series. Then the coupling only function of the unique parameter tau. It is modular forms, and it is some special forms. So I briefly review the modular inverse series, and this have been clearly given in the Fruitless paper and given by and the Ferrara paper. And we work in the n=1 global SUSIs and the modular inverse actions, including the Kähler potential and the superpotential. And the Kähler potential, we choose the minimal Kähler potential. It is not completely fixed by symmetries, by modular symmetries. In principle, there are many other terms, many other symmetry allowed terms. For example, we can add y dag y. Y is a modular forms. So this one is a drawback of the modular invariant approach. But here this is open questions. We usually take to be the minimal forms. That means the first term, the h lambda term is for the connect term of the complex modulars. The second term is for the connect term of the chiral fermions. And the Yukawa terms for the mass is described by superpotential. It has to be modular invariant. It is a polynomial of the chiral superfields phi I, I1, I2, I3. Label it's a label. It's collection of the quantum numbers. It can be the left-handed lepton fields or right-handed lepton fields, and it can also include Higgs. But we have to including another part. It is a modular form. It is a function of tau. It is a modular forms. Under the modular symmetry, the superpotential have to be invariant. That means the modular form is it is in the repetition of some finite modular groups up to some automorphic factors, theta plus d, some power of theta plus d. And the matter fields also transform in a similar way as the modular forms. It is in some repetition of finite modular group, and it carries some modular forms, modular weights. That means the repetition, the transformation of the matter fields, both matter fields and the modular forms are denoted by two quantum numbers. One is a ki, is a modular weight. Another one is repetition on the finite modular groups. And the modular invariance requires the total modular weight have to be vanished, and each term has to be invariant under the finite modular groups. So this one have be everyone is very familiar with this procedure. And in the original work of Fruitless, he concentrated on the even weight modular forms. So I have to say a few words about modular forms. Modular forms are holomorphic functions, and they transform in some special way under the modular transformations. That means under the modular transformation, there's the automorphic factor theta plus d case power, and the theta plus d is automorphic factors, and they satisfy the cocycle relations. And the n is a level. It's usually called level. It is usually called level. It is positive integrals, and it defines the principal congruous subgroup. It is a normal subgroup of modular SL2Z, and the modular form span linear spaces. The with key modular form and the level n span linear spaces. It can be decomposed into the irreducible partitions of finite modular groups. And if we concentrate on the even weight modular forms, then it would be irreducible multiplet of the inhomogeneous finite modular group gamma n. It is a quotient of the projective modular group gamma bar. It is over the projective principal congruent subgroups, and they satisfy these multiplication rules. We including Tn's power equal to 1, but for n larger than 6, we have to include another other constraints. And so far, the homogeneous inhomogeneous fundamental group have been widely studied from n equal to 2, n equal to 3, n equal to 4, 5, 7. So all these have been studied. So this is the most constrained part, and many models based on have been constructed to explain the lepton mass, lepton mass and mixing angles, and also applied to construct dark matter models and study the phenomenology of leptogenesis and so on. And now I want to study what we have developed on this formula on this modular invariance approach. First one is we extend the modular forms. The modular form we can extend from even weight to integral weight. Why only even weight? So we have to start from the SL2Z. It is known in SL2Z. If we study, we discuss the modular form of SL2Z, it has only even weight, and all the SL2Z modular form can be generated by E4 and E6. E4, E6 are Eisenstein series, and no odd weight modular forms. The reason is very simple. We consider the S modular transformation of S squares. So ST is a modular generator. So S square is -1. So under the S squares, tau is invariant. So according to the definition of modular forms, we get y S squared tau is y tau, and it is a C tau plus D case power. So it is -1 case power. If y tau is non-vanished, k have to be even. So -1 case power equal to 1. So no odd weight modular forms. But here, in the modular invariant approach, we consider the modular form of level n in not modular form of SL2Z. So for modular form of SL2 for level n, the odd weight modular form can exist because S square not belong to gamma n except n equal to 2. So if not n equal to 2, the odd weight modular form must be exist. And similarly, we can prove the odd weight modular form, or more generally, because the modular form is the modular form a ring. So all the integral modular form can be generated from the lowest weight 1 modular forms. So we generally discuss integral weight modular forms, and all the integral weight modular forms can be organized into irreducible representation of the homogeneous fundamental group. The homogeneous fundamental group is also defined by quotient of SL2Z over the over the principal congruent subgroups. So difference is S square is not equal to 1. It is a -1. It is different minus. It is different 1. So this is difference between the homogeneous fundamental group and the inhomogeneous fundamental modular group. So if we identified R equal to 1, that means we perform quotient of gamma prime homogeneous fundamental group over its center generated by R. Then we get the inhomogeneous fundamental group. So I generally called the gamma n prime. The homogeneous fundamental group is a double covering of the inhomogeneous fundamental group. And this is only structure is similar. That means the structure, the double covering is a 2 element correspond to 1 element. So in this sense, it is broad sense of double covering. And also the modular form have strong constraint. For example, we consider gamma equal to S squares. It is -1, so we consider the definition of modular forms gamma equal to S squares. From definition of modular forms, we get for modular forms, -1, the case power -1 times its repetitions, the repetition of R squared or R, it have to be 1. That means for odd weight modular forms, it have to be repetition of R equal to -1. It is in the spinor repetitions. For even weight, K equal to 2, firstly considered considered in the original works, then R, the repetition of R equal to 1, so it is vector repetitions. That means gamma n prime reduced to gamma n. So this is the first development. And all the integral weight modular forms can be constructed from the dedicated functions and clean forms for n equal to 3, 4, 5, and it is quite it looks not so complex, except n equal to 5. It is a complex. It is the Killing form somewhat it very complex. And then on the the double covering of finite module grouping not so widely discussed, but it has many interesting properties, at least from top-down string constructions. They gave the they gave the gave the gave the gave the homogeneous finite module group gamma n primes. So this is the first development along the weight of modular forms. Then we further extend the integral weight to fractional weights. So as a simplest examples, we consider the half integral weight. So the question is how we define the half integral modular forms. So if we don't consider the first side, we just need to extend the definition of modular form y gamma tau under the modular transformation. There is the automorphic factor c tau plus d's case power appears. Then for half integral weights, we just need to replace k is some k over 2. K is the integral, positive integrals. And this is intuitively we want to define the half integral modular forms, but this is not correct. It is wrong. The main problem is the c tau plus d, the k over the power of c tau plus d k over 2 is not the automorphic factors, and they don't satisfy the cocycle relations. That means that this definition, the question mark, the definition labeled by question mark, is not consistent. Is not a consistent definition. It is bad definition. The main problem is you can see if we perform two modular transformation, gamma 1, gamma 2, then you can see the inconsistency immediately, because you can see it's usually labeled with jk over 2. It is an automorphic factor. It not satisfy the cocycle relation. If the psi not appears for k equal, if the even integral for integral weight, then this psi equal to 1. You can see chi equal to 2 even. You can see this psi is two cocycle relation, two cocycle functions. It is a complex it's complex functions. So if it is half integral, this factor present, it cannot it not correct automorphic factors. Another issue is if it is a half integral, for example, k equal to 1, the simplest one, that means the root of c tau plus d. It is a complex function. It has two branches. It is Riemann surface. So how to define, how we choose the branch? So this is another issue. And this problem has been solved by mathematician Shimura. It is a great mathematician in 1973. The idea is we include both branches of the complex square root. The both branch different in minus psi and plus. This is different. So we extend the SL2Z to its multiplex coverage of MP2Z. Or not precise, it is not, or we can set MP2Z is a double covering, not two process of the SL2Z. The definition of the multiplexity covering is for each matrix for each SL2Z element, we compare with the theta plus d root theta plus d that we have gamma and minus plus theta plus root theta plus d. So for each element of SL2Z correspond to two elements of MP2Z. That means we include two branch or complex root complex square roots. And for here, the root, the theta plus d half power, we take the principal branch. That means its argument is confined in the range of minus pi to pi. Then the multiplication rule of P2Z is defined in this way. So gamma 1 tilde times gamma 2 tilde. The SL2Z part is same, gamma 1, gamma 2. But there is another part of the theta phi, theta root of theta plus d. So there is a psi ambiguity. And this one, in this way, we defined correctly. And the MP2Z can be generated also by two generators, S tilde and T tilde. For S tilde, we take one psi minus psi, so it is modular SL2 generator S, and compared by the minus psi of phi. And for T tilde, it is this form, and it satisfies the algebraic relation S tilde eighth power equal to 1 and S tilde T tilde third power equal to 1. So here, compare with SL2Z, it is S cube, S fourth power equal to 1. But here is S cube, S eighth power equal to 1. So it is 10. This is 10. And we can also define principal congruent subgroup. And for the half integral weight, it is only gamma 4n is meaningful. And the gamma 4n we defined in this way. And this also the element, it is the gamma 4n tilde, it is isomorphic to gamma 4n. And the element for the modular part, modular transformation part, H, it belongs to gamma 4n. But we have to carefully choose the psi of phi. That means choose the branch or the root or complex root carefully. And this branch is determined by the conic symbols. And it also arithmetic functions. Its value for gamma 4n is +1 or -1. Sorry. And we can also define the finite multiplicity groups. That is a ratio of MP2Z over over principal congruent subgroups. So similarly, is T tilde fourth power, 4nth power equal to 1. So we have to include another constraint. It is quotient because T tilde 4nth power equal to belong to principal congruent subgroup. So we include another multiplication rules T tilde 4nth power equal to 1. So this is the finite multiplicity groups. And but additional conditions are required for n larger than 1. And in this way, if we work in the multiplicity covers, then all the modular forms of half integral weight can be decomposed into the finite modular into the representation of finite multiplicity groups gamma tilde 4n, similar to the original modular inverse approach. But now we have to choose the gamma tilde, the multiplicity covers. If we still work in the SL2Z, then there will be a factor of two cocycle, these factors, two cocycles. Then it is not the linear representation, the modular form would be not the linear representations of the finite modular group. So by extending SL2Z and P2Z, we lift the projective representation to the linear representation. So this is the ideas. And for the and the according to definition of modular forms, we uniquely fix the multiply over the half integral with modular forms. It is defined by this one. It is a canonic symbols. So after we including these canonic symbols, then times the theta plus d, so k, the power of theta plus d k over 2, then this factor satisfies the consecutive relation. It is well defined. And we should also specify the transformation property of the modular of the matter fields. So it is phi. Here phi is this one, is a root of square root complex square root functions, and they have some modular weights, and they are in the representation of finite multiplicity groups. But here I want to stress, usually it is believed the modular weight can be arbitrary in original modular inverse approach, but not. But here, after we consider the half integral weight modular forms, we realized the modular weight of matter fields cannot be arbitrary. For example, if it is a half integral, we have to face the question of multiple values of the theta plus d. So if we consider fractional weight modular forms, in principle, we should consider the multiplicity covers of SL2Z, not SL2Z. And similarly, we can define other fractional weight modular forms. For example, weight 1 over 5. That means k over 5. And this for this group, it can only be defined over n equal to 5. If n equal to 5, it can be gamma 5. This only can be defined. Similar to half integral weight have to be 4n. For n equal to n is a multiple times of n. And for fifth power, for k over 5, you have to define the principal convolution subgroup. The level n have to be the some 5 times some integral, and this is usually the lowest order of the fractional weight modular forms. And you can see, if we consider, and all these have been constructed, the modular form have been constructed especially by mathematicians. And the question is, the property is not so good, because if we consider high weight, if we consider fractional weight modular forms, the order of the finite multiplicity is large. You can see for the n equal to 7, it will be 1176, too large. So this is the modular weight we can consider. In principle, you can also consider non-rational weight modular forms and complex weight modular forms. Then the group will be much more complex. It is called the universal coupling of the SL2Z. The second development is we consider the multiple modulars. The motivation is in string series. It is our universe is 4 dimensions, and the 6-dimensional is compact. So after we perform compactizations, then the extra dimension would be 6-dimensional Calabi-Yau manifold. So the effectively Lagrange is obtained by integrate over the 4 extra dimensions. So the resulting effectively Lagrange in our universe will be depend on the geometry shape of the 4D Calabi-Yau. So it is not single tau, but multiple tau. For example, 3 tau, tau 1, tau 2, tau 3, and this is the motivation. And the simplest possible cases is factorizable modulus. That means the 6-dimensional extra dimensional spaces is compactified to 3 torus. This is the simplest one cases. But here we want to consider the non-factorable, the simplest non-trivial non-factorable cases. It is single modular groups. And the idea is it is a quite natural generalizations. For modular group, it is G equal to 1 cases, and the single modular group is a G high genus. It is we extend SL2Z to SP2GZ. If G equal to 1, the SP22Z is isomorphic to SL2Z. Exactly the same. So we only need to the SL2Z, each element A, B, C, D, it is integral element, it is integral number to integral matrix A, capital B, capital C, capital D, and this satisfy the symplectic conditions. That is, this is the transpose of gamma times the modular single form G, and gamma is a G. And this is the definition of the single symplectic group. Then the complex modular tau is generate to a matrix. It generate to a symmetric matrix. It is transpose equal to itself, and its real part is positive definited. And so at the lowest order G equal to 2, it will be a 2 by 2 symmetric matrix. So it have two complex modulars, diagonal one element, two element, and the off diagonal one. And the modular transformation is also straightforward generation A tau plus D over C tau plus D into capital A times tau plus capital B, plus the inverse of capital C tau plus D. And we also need to decompose. That means we also need to decompose the modular forms we are into the irreducible. We want to decompose the modular group, the single modular group, into its congruous subgroup, principal congruous subgroup, and the finite group. So we can also define the principal congruous subgroup that model N. It is the identity. So it is exactly the same, and the principal congruous subgroup is a normal subgroup of finite index. So we can perform quotient. So we get the finite modular groups, finite single modular groups. And similarly, we can define the modular forms. We can get a modular form. We only need to extend the automorphic factor C tau plus D case power to determine C tau plus D, determine capital C tau plus D capital D case power. So it is very straightforward generation. And as an example, in this talk, I only I only talk the simplest generation single modular forms. For more general cases, we can generalize the modular form to automorphic forms. Then it would be defined in some Hermitian positive Hermitian spaces, positive Hermitian domains. So it is much more generally than the symplectic symplectic modular forms. Now the idea is if we consider lowest non-trivial cases G equal to 2 and N equal to 2 cases, then the finite singular model group would be isomorphic to S6, and it have no three-dimensional representations. It have only one-dimensional, five-dimensional, the nine-dimensional, 10-dimensional irreducible, the 60-dimensional irreducible representations. So we cannot build realistic models because we only have 3 generations of fermions. So we have to how to deal with this problem. We go to the subspaces of the finite single model of the finite space. We go to subspaces of the multiple modular spaces. That means we play in some smaller spaces. Then accordingly the finite modular group would become smaller. It can have smaller finite dimensional representations. For example, with 3-dimensional representations. So we consider the 3-dimensional. We consider the in equivalent. We consider the subspaces. It is very fortunate. All the invariant subspaces of G equal to 2 cases have been systematically classified by Gottlieb, the German mathematician, in 1991. So we are interested in the 2-dimensional and the 1-dimensional. It can have 2-dimensional subspaces, 1-dimensional, and 0-dimensional spaces. For the two-dimensional subspaces, there are only two cases, two independent ones. The first one is factorizable cases. That means the tau 1, tau 2, the diagonal cases, and the off diagonal is vanished. That means it is factorized two torus, but the two torus can be connected by some mirror symmetry. So this is different from naive factorizable geometries. And these two-dimensional subspaces can be obtained in string series. This has been showed by Peter and Patrick and Peter's group and Patrick's group. The second non-trivial two-dimensional spaces is this one. Is a diagonal one. Diagonal modular is equal. So one modular is tau 2 equal to tau 1. So also have two complex modular, tau 3, and this relative finite multiple group is as for cross C2. It have three-dimensional rotations. But for the first cases, you have no have 1 plus 2-dimensional rotations. So this one can be, the second one can be used to model building. Of course, the first one can also be used. And for model building skills, you can see these papers about the automorphic forms. And also we have one-dimensional representations. It only involves on one complex modulus. So this is for the complex modulus. And I want to talk another extension. That means in first cases we extend the modular weight and the modular symmetry itself. Now we extend the modular symmetry by CP, and this is quite straightforward because the general CP have been studied, have been initiated by Fruchley and studied a lot. So it is quite after proposed the modulus after the modular inverse approach, it is quite easy to think, oh, we can extend the modular symmetry or flavor symmetry with GCP. So the idea is so it's quite straightforward, but it's quite powerful because after we include the GCP, the symmetry is enhanced and the symmetry will become more constrained. And this has been studied before the modular inverse approach. The CP consistent with modular symmetry have been studied in string series by Peter and Patrick et al. Peter and Patrick's group. And he established the unique CP transformation consistent with modular symmetry is a top transform to minus tau star. So up to a modular transformation. If we perform another modular transformation, the combination of CP and the modular transformation is still a CP transformation. So the modular transformation have strong constraint on the CP transformation. And it is known the CP transformation is automorphism of the flavor symmetry group. So if we consider the CP transformation, we have to consider, if we want to define the CP transformation, we have to consider the automorphism of the modular flavor symmetry groups. For the SL2Z, they have the outer automorphism of SL2Z have only two outer automorphism. So you can see the U gamma, it is the automorphism of SL2Z. It is a product of two automorphism. First one is chi gamma, it is the homomorphism of SL2Z. So it is a plus one, it map each element of SL2Z into plus one minus one. The second one is the obvious homomorphism because it is similar transformation. It preserves the structure of SL2Z, right? So it is so this is looks quite obvious. So the product of two automorphism generate the whole outer automorphism of SL2Z. So we can see there are only two automorphism. That means because there are only two characters, the character have to preserve the multiplication rule of the ST. That means as false power equal to 1, ST third power equal to 1. So we can get only two characters. The first character is a trivial character that it maps all the element or equal to it identity map. It maps all element equal to 1. The second one is a non-trivial character. It maps both S and T into -1. So the action with CP on the action with CP on matter superfields. So we define this one. So CP under CP, the phi is mapped into its Hermite conjugation. Here is a superfields. So it maps the left-hand carrier superfields into right-hand carrier superfields. And XR is a unitary matrix in flavor spaces. So the form of XR depends on the repetition of phi. How three-dimensional, two-dimensional, or others. And we can apply the consistent chain. That means we perform CP and the modular symmetry and the inverse CP. So totally we should get it should be the effect should be a flavor modular symmetry because CP inverse. So the space-time coordinate is not changed, and everything for consistent it should be a flavor symmetry. It should be a modular symmetry. It should be a U gamma modular symmetry. So this is when we apply these consistent chains on modular on matter fields, we get the consistent condition chains. So this is the most general consistent conditions for SL2Z. So different this is the consistent. Then we discuss and this consistent condition chains determine the CP transformation of XR. So by solve this condition, we can get the allowed form of XR in specific in your chosen work basis. And in practice, we only need to consider gamma is S and T. That means we only need to consider two consistent conditions for gamma equal to modular generators S and T. Then we discuss because there are two possible CPs, two possible CP, so two possible automorphisms. So we can define two possible CPs. So we analyze the two possible CPs one by one. The first CP is here. X1 is a trivial character. It maps all elements equal to 1. So chi gamma equal to 1, we obviously get this one. So it maps as inverse T into T inverse, and chi gamma equal to 1. So we get a consistent condition. We map as into inverse T into T into T inverse. So this one is a class inverting automorphism generally. And in the symmetric basis, that means both ST repetition matrix is symmetric. Then we can solve this condition. You can see obviously because S inverse is a Hermite conjugate. So we got XR is an identity matrix. So it is a canonical CP. And in this basis, it will be constrained. All the coupling will be real. So this is usually discussed in the literature, the first general CP. For the second CP, the second GCP, it is defined by the non-trivial character. They map ST into inverse. So we get the consistent condition. We from the most general consistent condition, we get the consistent condition for the second CP. For second CP, you can see there is a factor sigma. And this factor sigma is determined by the modular weight of the matter fields and its repetition assignment. The repetition assignment. So generally, it can be the sigma have to be +1 or -1 because the key phi is the integral and rho r s1 r square is the center. So it is also +1 -1, and s cube is equal to 1. So you can see the second GCP depends on the weight and the repetition assignment of matter fields. The only new thing is sigma. The assignment for the weight and repetition is sigma equal to -1. If sigma equal to +1, it is reduced to the first CP. So for the sigma equal to -1, for example, for n equal to 4, we can choose the R two-dimensional repetitions, and the k phi is an odd number. Then we can get the sigma equal to -1. This is non-trivial. This is non-trivial second CP. And we solve the consistent condition, we can get the level n have to be even because we can take the Tn's power equal to 1. This follow from this condition. And the dimension of the rho n have to be even. And we can take this one is take determinant of this follow from the determinant of the consistent condition. And the third one, the trace of the both S and T have to be equal to zeros. You can take the trace on both sides of the consistent conditions. So that means the sec CP have very strong conditions if you want to define sec CP, and the sec CP only for the matter fields. For the modular forms, it only I have shown only sigma equal to +1. So only k n equal to even. So the lowest one is n equal to 2, and the rho r have to be even dimensional rotations, and the repetition trace the character have to be zeros. So the sec GCP, sorry, because I have mistake time. Someone not delete, not delete. And so the sec GCP transformation, the constraints, you have strong constraints. And you can see if we take the -1, that means if we want to impose sec CP, we can only assign the 3 generation fermions to 1 plus 2. 1 plus 1 or singlet, the direct sum or singlet and doublet. And both right-handed and right-handed have to be plus to belong to the same GCP. Otherwise, the minus C cannot be cancelled. This is crucial. So if we including the sec CP, would be constrained the Fermi mass matrix would be block diagonal and some miss angle are managed. So the conclusion is even if there is the sec CP exists, but we don't need to consider sec CP because it cannot accommodate the present date on flavor mixings. Then we come to the CP conserved value of modulus. That means in the upper half plane, not all the tau is the same. Some tau are quite special. It know there are four CP four modular fixed point. It is ohmic and minus ohmic squares, minus ohmic squares, and tau equal to I and tau equal to infinite. It is invariant under some modular transformations. Similarly, we extend the CP transformation, modular transformation. So we want to consider some special value of tau not invariant. It is invariant under the CP transformation. That is minus tau star equal to gamma tau. There are only 4 possible cases because we only need to consider in the fundamental domains. So for only to 4 cases, gamma equal to 1, we got tau minus tau star minus tau star equal to tau. So its real part is 0. So it is tau is purely imaginary. It is imaginary access. For tau equal to t, we got it is the real part of t is minus half. So it is the left boundary of a fundamental domain. For t equal to for gamma equal to t inverse, the real part is half. So it is right side of fundamental domain. For tau gamma equal to us, we got the absolute value of tau equal to 1. So it is the arc of the fundamental domains. So this is compress. This is the module. This is the CP conserved value of tau. Hello. Can we break a few minutes? And if you have any questions, we can discuss.
Yeah, we can take a break. Or are there some questions? Maybe if somebody has a question, we can first discuss the question. Does not seem to be the case as far as I see. So
in first part, yes.
So this was the first part. So let's have a break and let's make it not too long. Let's meet again at 1:05.
Yes, you show how to extend the possibility of integer, even integer, and then eventually fractional weight. And I have not followed completely your explanation, and I would like to know whether when K is a fractional, so fractional modular weight, if modular forms and matter multiplets still transform, have the same transformation properties, or there is a difference between modular forms and matter multiplets as far as transformation are concerned.
The question is, maybe I don't understanding completely your questions. The key point is here, how to define the modular forms. You cannot just change the k's power, k is the integral, to k over 2. It's not correct. This definition is not consistent because they don't satisfy the cosecant relation. That means if you perform two gamma 1, gamma 2 simultaneously, it should be equal to c tau plus d, k's power over 2. The c tau is gamma 1 c, gamma 1 times gamma 2 c, and d is gamma 1 over gamma 2 d. But it's not, because there is a this factor, 2 cosecant relation, you can see. So it's not consistent. We have to extend. Do you agree with this one? You
Yes,
understand this one?
This I have understood. Yes, thanks.
Yeah. So this, we have to include some factors, right, to make it satisfy, to make the definition consistent. Then how to define these factors? I show you this one. For the half integral weight, this factor is VH. VH is +1 or -1. That means we have two branches. The K, it is complex functions, right?
Maybe
so
if you can go back to the slide where you explained this point. Yes, yes.
We have to include a multiply, right? VH. So to make a definition, to make the modular form is consistently defined. Then, if we still confined on SL2Z, then you can derive the modular form would be the projective representation of finite modular group, not a linear representation, because this factor, because this psi. Because this psi.
Yes.
So we have to, after we extend the SL2Z to MP2Z, this projective representation, the modular form is projective representation of SL2Z, or finite modular group of SL2Z. If we extend SL2Z to the multiplex coverage, that means including both branch, you can see gamma and +1 - 1 root. The phi is +1 - 1, both elements, one gamma correspond to two elements of MP2Z. If we extend the SL2Z group, then the modular form will be the linear representation of finite multiplexing group. So we extend to multiplex group just to form the finite linear representation. This is another key point.
If I might comment, so if I understood Ferruccio's question correctly, if you go one transparency further,
This one,
the next one,
this one.
yes, I think there is the Yukawa couplings and the matter fields. I think they transform the very same way. In the box, the Yukawa couplings, and then 2 lines below the matter fields.
So firstly, I can give you the conclusion easily. I can let you understand it easily. You have to specify, that means all the matter fields and the modular form are specified by the representation of modular group, right?
Yes.
So you have to, the definition of transformation have to be consistent. This is the key point. If you still work on SL2Z and the automorph factor is c tau plus d k's power, then you can see that means you replace phi is c tau plus d, root c tau plus d. Then you will get this one. So the 2 theta plus d times, you can see this one, also perform 2 modular transformation. You will not consistent. There will be a factor 2 cocycle appeared.
Okay, yes.
You can see here, JK, you first perform gamma 1, then perform gamma 2, you get the last 2 terms. It is not G1 gamma 1 gamma times gamma 2. There is another factor, it is 2 cocycle. You can times 2 cocycle from both sides appears, not consistent. The point is the 2 cocycle is plus 1 or minus 1. It is related to branch or square root. The idea is given by Shimura. We including both branch or plus 1 or minus 1 branch, minus 1 factors. Then this factor would be disappeared. Some element of MP2Z satisfy the cocycle relation.
Okay, and you apply this both to modular forms and to matter multiplets.
Yes, because this comes from this one. The theta plus d to its power over 2 is not to satisfy the cocycle relation. So if involved the theta plus d, the power of theta plus d's power k over 2's power, you have to face this problem.
Okay.
It's not relevant to either matter fields or modular forms.
You have to change the automorphy factor for matter and for modular.
Okay.
Forms.
Thank you. Thank you.
Yeah, this is a key point. You have to be consistent. So this is a consistent constraint.
Okay.
I don't know whether we still have the time. Can I also ask my question, or should I postpone it to later?
Your question? What's your question?
My question was whether you always have modular transformations with fractional weights. I'm also in the case of fractional weights. If you always have modular transformations that actually act trivially on the moduli. If you extend now to the metaplectic cover, whether
Yes.
this group always contains transformations which act trivially on the moduli.
Or trivially act on the modular.
If some of the elements of gamma tilde act trivially on the moduli.
No. It acts in the same way as gamma on the modular. Not trivially.
But some of the elements, not all of them. I mean, is there now a bigger subgroup? Normally, S squared acts trivially. The modular S transformation squared acts trivially on the moduli.
You are right.
Now you
Yes.
extend to the metaplectic group, and my question is, are there more transformations which act trivially on the moduli? For example, a transformation where gamma is identity, but phi is still -1.
You are right. You are right. For example, as squared, as fourth power, as sixth power.
Okay, so in this way, in the metaplectic group, you extend the modular group by transformations which leave the moduli invariant.
Yes, there is some subgroup. It is center. It is center of the group. It is generated by S squares. So under this center, S square generated by it is Z4 subgroup. The moduli is invariant.
Okay.
You are right.
In this way, it connects to the traditional flavor symmetries which do not act on the moduli, I would say.
Yes, it can connect with your eclectic flavor group. So it is a Z4 is a Z4 is a traditional flavor symmetry group.
Thank you.
But from top down, I don't know how can naturally connect. Can you interpret? Can explain the Z4R, the Z4 subgroup generated by R as a flavor symmetry group?
So we always have these fractional modular weights for some of the matter fields. not for the modular forms. Our modular forms always have integer
Yes.
weights, but the matter fields, they always have fractional fractional weights, and they connect to some of the string selection rules. So we have this situation of fractional weights, and they are connected to the string selection rules.
And you have to you have strong constraint on some. You have some Z3 or Zn subgroup to absorb the phase, right?
Yes.
But here I'm from top down, bottom up. I just I don't consider more additional input at high energy scales, right? You have assumed other element, another Zn subgroup to make you consistent. But here I don't have such element, right?
Yeah, but it's curious that you also introduce traditional transformations now by using these fractional weights. So
yes.
Also starting to mix modular symmetries and traditional symmetries.
But here the modular symmetry commute with the traditional flavor symmetry. It is the for commute in center. So this is trivial in your views or electric flavor symmetry group. It is trivial.
Okay,
it commute. So then I continue my talk about CP symmetry, and I have said if the tau is purely imaginary or at the boundary fundamental domain, this tau is quite special. It is invariant under some action or radial CP. Under some, it preserves some of the radial CP. So I discuss the implication of radial CP, and this is a superpotential for the Lepton mass term and neutrino mass terms, and the modular invariant require the Yukawa coupling have to be transformed in this way, and the CP invariance would require the modular form, the Yukawa coupling their modular forms transformed in this way, and this is the CP and modular requirement of CP and modular invariance. And if we work, if the tau is at the CP conserved values, it is at the boundary of purely imaginary, that means the minus tau star equal to gamma tau. So we can see these two equations. We will get constraint on the Yukawa couplings. So at this one, we will get at this CP conserved point, both neutrino mass matrix and Lepton mass matrix would preserve the same CP transformations. They are invariant under the general CP transformations. So we would, and the implication is the Lepton mixing CP with the CP violation phases in the Lepton mixing matrix would be trivial. And this have been given by in the original papers on general CP. And I also want to. So if you want to explain the data, the modular tau have to be departure from the CP conserved port, and the departure is very small. Small departure is enough to generate large CP violations. It has been proved in many models. And another one I want to include another point is, if we consider the CP violation at high energy scales in leptogenesis, that means if we still work in the if the tau is still fixed at the boundary, then the CP violation, CP symmetry in the leptogenesis would be vanished. So we have to the departure from the CP conserved point can also help to explain the matter symmetry in leptogenesis. And then I want to talk about the phenomenology about the modular symmetry. Mainly the advantage of modular symmetry. The modular symmetry is in that at first look we can see modular symmetry have finite modular groups. It is a homogeneous or inhomogeneous finite modular groups. So it naturally include the non-abelian finite flavor symmetries. But the flavor symmetry, modular symmetry have infinite element. So modular symmetry have more than the traditional flavor symmetry, and they combine. They have the merit of both appealing and non-appealing flavor symmetries. Now I want to emphasize its the part of it can realize the non-appealing flavor symmetry. For example, U1 appealing flavor symmetry in some sense. The first one is a modular symmetry can generate texture zeros. A texture zero is important, is a simple answer to reduce the parameter of the mass matrix. And if we impose some texture zeros, for example, for each textures, we can relate the mass ratio over the mixed angles. But usually, before the modular symmetry, it believes that to produce the texture zeros, we need to use appealing flavor symmetry, for example, U1, and some elements are highly suppressed. So this is a usual idea. But after the involvement of the modular inverse approach, we found the modular symmetry can naturally generate texture zeros from the mathematical structure of modular forms. After we consider the integral weight modular forms, the odd weight modular forms always in the representation of S square equal to -1. That means it is in the spinor representation of the homogeneous finite modular group. And for the even weight modular forms, they always in the representation of S square equal to +1. So this is a vector representation. That means the odd weight modular form in the representation different from the inhomogeneous modular group, because it is homogeneous modular group is double cover of the inhomogeneous modular groups. For example, we consider n equal to 3. That means the inhomogeneous modular group is T prime. It is a double cover of A4. So they have spinor representations, 2 prime and 2 double prime. They have 3 two-dependent representations. It is spinor representations. And they also have representation of A4. It is a vector representation. It is a triplet and 3 singlet, 1 prime and 1 double prime. So this structure of modular forms can be used to generate texture ruler exactly. For example, we consider the quark setter. We assign the 3 generations of quarks to doublet plus singlet. The first 2 generations assume to doublet, the third generation to assign to singlet, because the third generation is quite heavy. And we can choose the weight of the modular forms, choose the weight of the matter fields to make it exactly zeros. For example, we consider the up left blocks. It is a contraction, some modular form contraction with the first 2 generations left-handed quark and right-handed quarks. But 2 times 2 form T prime, they have to be transformed with 1 and singlet or triplet. That means they have to be contracted with some modular form in vector representations. But if we choose a modular form, the weight of modular form, that means it is determined by the sum of the KD plus KCD. If it is odd, there is no odd weight modular form in vector representation, so it is exactly zeros. This is the idea. So it is quite simple. That means we can use a structure or modular forms can generate zero exactly. And in this way, from n equal to 3, the lowest cases, we can generate 5 texture zeros or quark mass matrix. And this is we name the A, B, C, D, E up to the permutation of row and columns. And this is different from previous approach to produce texture zeros from appealing flavor symmetry U1. And now the texture zero come from the mathematical structure. It is protected by mathematical structure of modular symmetry, by structure of modular forms, not assumptions. And the non-vanished element, that is the cross one, it is correlated with each other, not arbitrary. In previous U1 appealing flavor symmetry approach, it is arbitrary. The second one, the modular symmetry can generate can play the role of the appealing symmetry is a White mechanism. This is proposed by Steve. The idea is the modular weight. Besides the finite modular group, we also have modular weights. The modular weight free in some sense. For example, if we consider the homogeneous finite modular groups, the modular weight have to be integral and unintegral. The modular weight can play the role of the Frogat-Nielsen charge. This is the ideas. For example, to show this idea, I start from the original models, original A4 modular models by Fruchli, and this is his models, and the left doublet is assigned to triplet, and it's carry modular weight 1, and the right-handed lepton the transform as 1 double prime and 1 prime, and they all carry 1 unit of one unit of modular weight. And the right-handed neutrinos, the A4 singlet, A4 triplet, and 1 unit modular weight, and the Higgs singlet, both are A4 singlet with 1h modular weight. So this is the superpotential for the Chern-Lepton mass matrix, and we can write out this mass matrix, and we take the tau as a free parameter to fit the data, and this model can explain the data, can place lepton mass and the neutrino mass and mixing the data with neutron mass and mixings, and the tau is the imaginary part of tau is larger than 2, so it is quite large. That means the tau is 10 to F infinite. It is large volume limit. Then in this limit, at the wide ball point, phenomenology wide ball point, we can get the Chern-Lepton mass matrix is approximately proportional to, is approximately diagonal. It is proportional to alpha beta gamma. So to explain the hierarchy mass of electron muon tau, we have to require alpha much smaller than beta and much smaller than gamma, and this is also reflect in the data fitting. So the idea is how to generate the mass hierarchy. That means this model do not explain the hierarchy mass or electron. The electron hierarchy mass or Chern-Leptons. The Chern-Lepton mass hierarchy are obtained by tuning the coupling constant alpha beta gamma. They are not order 1. So the Bethe models is the idea of Bethe model is we include another flavin. It is called Bethe, but this flavin is very special. It is singlet or standard model singlet, A4 singlet, only carry non-zero modular weight. That is in flavor singlet. It's not different. It is different from Frogat-Nielsen flavins. Frogat-Nielsen flavins carry U1 Frogat-Nielsen charge, but here it doesn't carry A4 charge. It only carry 1 unit modular weight. So after include this one, we can reassign the modular weight of the matter fields to let them couple with certain power over the Bethe. For example, EC couple with the phi tilde force power, the mu C couple with the phi tilde tooth power, and the tau C is coupled with phi tilde. Phi tilde is phi over some cutoff scales. That means the alpha beta gamma is suppressed by different power of Bethe. So in this way, we can explain the mass hierarchy, and the coupling alpha beta gamma is same order. So this is Bethe. It just looks like a simple and beautiful mechanism. Another possibility is the hierarchy Fermi mass. Hierarchy Fermi mass could possibly come from some modulars very close to certain fixed point. We only consider the flavor the modular symmetry fixed point at the four modular fixed point, the gamma equal to ohmic or minus ohmic squares, tau equal to tau equal to I imaginary I, or tau equal to I infinite. And around this fixed point, there is some radial symmetry. Z are billion radial symmetries, and the small deviation. So the Fermi mass matrix would be parameterized by the deviation by the small deviation by the power of the small deviation from the CP fixed from the fixed point. But in this approach, it seems that more free parameters are involved. So it looks not so predictive. Maybe I understanding wrong on this part, but from the fitting from the defeating, it seems that more free parameter required to make to explain the mass hierarchy, and all the and the involved parameter is the order one. The second point is another point I want to explain the another development is on modular symmetry, the quark-Lapton unification. Here I want to give a split example based on double cover or S4. Here is the idea is we want to explain the quark Lapton mass and the flavor mixing simultaneously in a symmetry work. Now, the flavor symmetry is a double cover S4, it is S4 prime. Lapton is the left hand Lapton is triplet. The left hand quark is also triplet, and the right hand neutrino is triplet. So quark and Lapton seem quite similar. They are triplet, left part is triplet. At the right fields, right-handed Lapton and the right-handed quarks are all S4 prime singlet. So it looks like symmetric, not so symmetry, and not exactly the same, but they are also singlet. They are all singlet. The Higgs is singlet or S4 prime, and with vanished modular forms. And we including GCP to enhance the predictive power of the model. So after including GCP, all the coupling constant in our working basis would be real. Then firstly we consider Lapton sector. So the structure is quite similar to the Fruchtley's original model, original A4 modular models. It is also, you can see, but it is much simple. The Lapton sector have 3 terms, as I have said previously, quite similar. But for the neutrino sector, it looks quite simple. You can see there are only appeared, the non-trivial structure only appear in the Dirac neutrino couplings, and the right-hand neutrino mass matrix is a permutation matrix. It's quite simple. It is constant proportional to P2-3 permutation. And this model have only 5 coupling constant and 1 complex modular tau. So totally 7 parameters. So it is quite simple. And this is I see as far as I know, this is the minimum model at present. Minimum modular models in Lapton sector have 5 couplings plus 1 complex modulus. Then I come to the quark sectors. The quark sector is also quite similar. You can see they only couple with different modular forms, but the structure looks similar. Each of them, the up quark sector and down quark sector, both up quark sector and down quark sector have 4 terms, and all the coupling constants are real because of GCP symmetry. So this is MU, MD. The structure is the same, but the different modular forms. They involve different weight of modular forms, and they have 8 real coupling constant. And the complex modular tau can be fixed by the Lapton sectors. So if we input the tau of Lapton sectors, the quark sector will be only dependent on 8 couplings to explain the 6 quark mass and the 6-3 quark mixing angles and 1 CP violation phases in CKM mixing matrix. And the complex modular tau is fitted to be the best fit value is here. It decides to be these values. Is this ones, and the best fit value or other input parameter is here, is this one, and then at the best fit point we can get all very good predictions for the mass and the missing parameters. Almost all the observable are within the 1 sigma readings, and the C23 is about is larger than 45, is in the second octet. It's about 0.556, and the third CP is close to minus pi/2, and the neutrino mass is quite smaller. You can see the neutrino mass is quite smaller. They are consistent with the present bound from Planck and Kachu. For the Bethe in neutrino double beta decay is also quite tiny. It's almost not possible to be tested in it's quite small. It's quite small. It is possibly in the marginal test in marginal sensitivity of the future neutrino double beta decay experiment. So this quark-Lapton unification models, we use only 15 parameters to describe all the mass at missing or quark-Laptons, including 12 mass and 6 missing angles and 3 CP phases. Totally, it is 21 parameters. So we have 6 predictions. And the prediction for the neutrino mass and the CP phases and missing angle are compatible with the parameter data of neutrino oscillation and the cosmologies. And this model could also possible to be tested in future models by measure the C23 and third CP and the neutrino double bit decays. And also, quark-Lapton unification model can be quark-Lapton unification can be achieved in other modular symmetries such as A4, but more free parameter are needed. Then I go to the another possible to extend the modular symmetry is a modular GATT. We want to combine 2 symmetry approach. That means the Fourier symmetry approach and the GATT symmetry approach. That means that the GATT symmetry can reduce the quark-Lapton, and the modular symmetry we give the Fourier structure of the Fourier structure of the 3 generations. So the GATT symmetry we work within the GATT symmetry. They work within each generation of fermion, and the Fourier symmetry, they related to different generation of fermions. And we work in SU5 GATT. In SU5 GATT, each family of fermion are unified into 2 multiplet. It is 5-bar multiplet, F-bar, and the template is a T. To explain the neutrino mass, we generate the neutrino mass by seesaw. So we including SU5 singlet. It is right-hand neutrino. So all the 15 multiplet plus 1 right-hand neutrino within each generation are unified into 3 multiplet, 3 SU5 multiplet. And we can classify all the possible modular SU5 models, modular A4. So we consider the simplest modular symmetry A4 and the conventional SU5 GATT models. And this is the most general superpotentials. And this first term is for the right-hand neutrino mass term. The NF bar H5 is for the Dirac neutrino couplings, and F bar T, this is for the Chern-Lapton mass matrix, Chern-Lapton at the down quark mass matrix, down quark mass, and to explain the mass difference between the up quark to explain mass difference between the Chern-Lapton sector and the down quark sectors, we introduce another Higgs multiplet H45 bar. If only for H5 bar, the mass spectrum of down quark sector down quark the Chern-Lapton will be exactly the same. It's not consistent with parameter data, so this is a reason why we introduce H45 bar to introduce the George-Jaskov factors. And the last term is responsible for the TT term is responsible for the up quark mass. And this you call this Fn, the Fm, Fn, Fd, Fd prime, Fu in each terms. And these are modular forms. They are determined by the weight and the repetition of the matter fields. So we can classify all possible models according to the repetition assignment of matter fields. We consider 7 type of models. So they classified according to the repetition of the N F bar T under the A4. And we consider first case is, for example, the first case is both N and F bar is assigned to triplet, and the T is a singlet, the one prime, one double prime. And but we don't consider all the fields N F bar T are singlet assignment, because it will be involved too many free parameters. The A4 symmetry will be not so effective if all the fields are assigned to singlet. And for the first type 1, type 2, type 3, type 4, type 7, type 5, we introduce 3 right-hand neutrinos. That is 3 right-hand neutrino models. And we also consider 2 right-hand neutrino models. It is type 6, type 7. So the 2 right-hand neutrinos, they are assigned to be singlet. And this is what we have considered the type of models. For each type of models, we can freely assign the modular weight to some integral, modular weight of matter fields to some integrals. So we can we can systematically consider all possible form of this Yukawa coupling. And we find there are, we pick out, we are interested in the model with the smallest number of free parameters, and we find 45 models, 53 models for type 1. Type 1 have 17 models, type 2 have 2 models, and this one, all these models are specified by the site, by the weight and the repetition assignment on matter fields. So they can be easily, from this table, we can easily read out the Yukawa superpotentials. And the prediction for the lepton CPY, the prediction is this model could possibly test in future neutrino oscillation experiment by long baseline neutrino experiment by the measurement of direct CP phases. And we plot the prediction for CP phases in these figures in clock scales. So all these models, here we including the 3 sigma region of the direct CP phases. So you can see the direct CP phase still scatter in large regions. So this model, it can be, I expect some of this model could be excluded by future by the measurement of future neutrino oscillation, by measuring direct CP. And this is prediction for the direct for neutrinos double Bay decay. And some of the model is already excluded by the neutrino by the cosmology data. So if you take the cosmology constraint from Planck seriously, because bound on some neutrino mass is sensitively depend on the data used, data analysis, and on the cosmology models. So I'm not sure how precise, how I can believe the cosmology constraint. So if we take seriously the constraint, some model is already excluded by the strength bound of Planck. So my talk is almost finished. I want to summarize my talk in this mind map. The modular symmetry is a very interesting ideas. It can overcome many drawback of previous approach, and it has been discussed by many. It has been discussed. It has been widely discussed. It has been developed in many different aspects. For example, the modular weight, they can even weight, integral weight, and fractional weight. The modular can be single modulus, the multiple modulus, and we can also extend the modular symmetry by CP, and we can combine the modular symmetry with gut symmetry to explain to understanding the flavor structures. And the phenomenology also being, there are many phenomenology papers and many mechanisms have been proposed. For example, the modular symmetry can have merit or abelian flavor symmetry. It can generate texture 0, and the Bethe to explain to Bethe mechanism, and to can build quark-Lapton neutrino models, can explain the matter symmetry, and so on. And and it can also, the modular symmetry can also combine with the flavor symmetry to get a more predictive predict the electric flavor group. And this topic will be discussed tomorrow So I don't cover this part because I'm not an expert on this topic. So this is my talk. I think modular symmetry is very interesting, but it's still at early stage of development, and many aspects should still need to be understanding. And there it also has some drawback. We need to develop and improve. Thank you.
Okay, thank you very much for this nice and comprehensive talk. This was very nice. So we learned a lot. Are there some questions?
Can I have a question?
Yes,
Yeah. Sky, hello, Sky. Hi.
Nice to hear you.
Yeah, nice to meet you. Nice to see you. See you. Hello.
Can you ask your question?
Hello. Hello. Can you
Yeah.
hear me?
Do you hear me?
Can you hear me?
Yeah, we can hear you. Yes.
Okay, so I ask the question. So in the model with texture zeros, where you have fields which have different s square, quantum numbers, -1, +1. Can you avoid the fine tuning?
Oh, this is not fine tuning. This is protected by I use this group structure of the modular form. This is not fine tuning. This is structure. For example, I can show you this one. I can see this one. This is this one. I just use this. I just use this property.
But can you have the mass ratios?
This one. I just use
For example,
this one.
Yes.
This one. Minus 1 case power minus equal to. Sorry. This one. Sorry. This one. The minus 1 case power times a square equal to 1. So old weight as square
mass ratio.
Mass ratio.
Ratios, I mean, which are very hierarchical.
Determine
modular form properties.
This is an interesting question. You ask me, I have generated texture zeros, but how I can explain the mass hierarchy within the framework of texture zero, right?
Right.
In my models, I generate texture zero, then fit the coupling constant. So some coupling constants still have to be large, and some constants still have to be small. So I have to be fine tune. I have to be tune the coupling, tune some couplings in texture zero models. Here, I have to tune the coupling of non-vanished element. Hello, Sky. Your why?
Working. If one tries to determine the mass hierarchies, working very close to these symmetric points, I omega, I mean the left cusp and I infinity, the case of I.
Hello, Sky. Your voice sometimes break down. Your
symmetric point equal to. That's all I wanted to say. Thank you very much. It was a very nice talk. It was a pleasure.
Hello, Sky. I know your. I think I can guess your question. In my models, I'm interested in the minimum in the model with a minimum number of free parameter and the texture zeros. If I consider some models with more free parameter, but still produce texture zeros, all the coupling can be of order 1. This can be achieved. But for minimum models with a small number of free parameter models, it's not possible in the texture zero.
Okay.
Even if we consider texture zero.
Thank you.
So sorry.
Steve King has a question.
Yeah, and on this slide about the texture zeros, well, phenomenologically, there is sort of some motivation for having a texture zero in the first entry of the mass matrix, the 1-1 entry. So if I understand, like the case D, for example, is it possible to reinterpret that texture zero as a 1-1 texture zero?
Exactly, because the texture zero is produced up to row and column permutation. You can perform row and column permutation in any way you want. So we can achieve 1-1 element vanish.
Okay, great.
Yeah. Oh, sorry. Yeah, you are right. Maybe this is quite misleading. The third generation is massless. This is not good. We should put the zero on the one element. Then people can understand. Can understand,
Oh, that's
right?
fine.
Yeah,
Okay,
yeah.
thanks. Yep.
Yes.
Are there more questions? Stefan, yeah, you have a question.
Yes, maybe slightly more mathematical. I was wondering about this generalization to fractional weights. Does it apply to any fraction or only half integral fractions?
Oh, this is you can see this table. You can see for half integral, n have to be multiple of 4. We have a strong constraint. We have strong constraint on the level. For example, for half integral, the n have to be n should be 4k, fourth power, multiple 4. For fifth power, for example, if you consider this one, the second row, k over 5.
Okay, so
then
you
n have to be 5.
Mm-hmm.
We have a strong constraint.
So for any fraction that you want, you need maybe a different n to accommodate. So for example, if I want to have fraction of 1 over 13 to have a strange number, I have to go somewhere down your table to find the right n to do so.
Yes, you are right. But if you go to other n, if you go to other fractional weight, the finite mathematical group will be quite large. You can see the last one is already 1,944.
Mm-hmm. So
yeah.
for the monology, you would say you only have to consider case n equal to 4 or also other ones?
For nomenology, we have considered n equal to 4, the half integral, and n equal to 5. And this can be produced from, and this can also be produced from string constructions by Michael and tomorrow's speaker.
Okay, thank you.
So yes, the first two have been considered. The other cases, it looks like too large for me. So I don't consider the latter two cases.
Okay, thanks.
Okay, there's a question by Titov.
Yes. Hello, can you hear
Hello.
me?
Yeah, I can hear you. Hi.
Thank you very much for your nice talk. I have a phenomenological question about the quark sector.
Yeah.
So you discussed an example, I think, within the modular S4, where you unify leptons and quarks.
Modular S4 prime.
Yeah, right. And if I understood correctly, in the quark sector, you need 8 coupling constants plus the modulus. So it's 10 parameters in total. To describe 10 observables in the quark sector. So
you are right. But
question, can you have less number of free parameters if you focus only on the quark sector? Let's forget about leptons. Can you have, I don't know, less than 10 free parameters?
These have been given in my S4 prime models. I can have 9 parameter models in quark sector, only for quark.
So this is the least number is 9.
At least at the moment, I only find 9 parameter models.
I see. So naively, it seems that it is not so actually easy to have a viable model with, let's say, a few parameters. I don't know, 5 parameters. Because now you see it naively, you try to explain 10 observables with 10 parameters. So I could say, come on. So,
but you are right. It's really not so easy to explain the quark sector with few parameters. But I don't disagree with your argument. I explain 10 parameter with 10 observable with 10 parameter because the tau is a common parameter in the quark lepton sector. So I can, in principle, I can determine the value of tau from lepton sector. Then only 8 coupling is left in the quark sector.
Okay, I see.
But it's not easy. I have to I have to admit, it's not easy
Mhm.
to explain the quark mass spectrum and mixing with 5 or 6 parameter. It seems at the moment I don't find such models, although I have considered thousands of models.
Mhm. Okay,
Yes.
thank you very much for honest answer.
Okay. Are there more questions? Well, I think it does not seem to be the case. So I think we thank again for this nice talk. And we will then meet again tomorrow afternoon, our time, for the talk of Saul Ramos Sanchez, who will discuss the top-down approach to modular flavor symmetries. Okay, thank you very much.